future of computing doesn't rely on zeros and ones anymore. What if a computer could hold multiple realities at once, solve uncrackable codes, revolutionize medicine, and create materials that haven't even been invented yet? It might sound like science fiction, but this isn't a distant dream. This is the strange and fascinating world of quantum computing, where the impossible becomes possible, and where the very laws of reality are redefined. In this video, we're going deep into one of the most mind-bending and potentially world-changing technologies of the 21st century, quantum computing. We'll break down what it is, how it works, where it came from, who's building it, and why it might transform industries from healthcare and finance to artificial intelligence and cybersecurity. We'll explore the weird science behind it, the challenges of making it work, and what this all means for the near future. This isn't just a story about computers. It's a story about the limits of human understanding and what lies beyond. To understand quantum computing, you first need to forget everything you know about traditional computers. In classical computing, everything is based on bits. A bit can be either a 0 or a 1. That's it. Just two options. Quantum computers use qubits or quantum bits. A qubit can be 0, 1, or both 0 and 1 at the same time. This is called superposition. Imagine flipping a coin. A regular bit is like it landing on heads or tails, but a qubit is like the coin spinning in midair, existing in both states until you catch it. Now add another phenomenon, entanglement. Two qubits can become entangled, meaning the state of one instantly affects the other, even across vast distances. Einstein famously called this spooky action at a distance. These properties allow quantum computers to perform multiple calculations at once, in parallel, unlocking a level of computing power beyond anything possible today. The idea of quantum computing has been around for decades. In 1981, Nobel Prize-winning physicist Richard Feynman proposed that if we want to simulate quantum systems, we should use quantum machines. At the time, it was just an idea. But in 1994, mathematician Peter Shor developed an algorithm that could crack encryption codes much faster than classical computers. This caused a shockwave in the cybersecurity world. Suddenly, the idea of a quantum computer wasn't just about science. It became a race with serious global implications. Governments, research labs, and tech companies realized that quantum computing could become a massive strategic advantage. Building a quantum computer is not easy. Qubits are incredibly fragile. They are sensitive to temperature, vibrations, and even light. Most systems have to be kept at temperatures close to absolute zero, colder than outer space. There are different approaches to building quantum computers. IBM and Google are using superconducting qubits, which are tiny circuits that conduct electricity without resistance. IonQ uses trapped ions, charged atoms suspended in a vacuum, and controlled with lasers. Other companies are experimenting with photons, the particles of light, or even atoms placed on silicon chips. Each approach has its strengths and weaknesses, but they all face one major challenge: error correction. Qubits can easily lose their quantum state, causing mistakes in calculations. To prevent this, researchers use many physical qubits to create one reliable logical qubit. This adds complexity and cost. So why go through all this effort? Because quantum algorithms can do things classical algorithms cannot. Shor's algorithm can break RSA encryption, which protects much of the world's digital communications. Grover's algorithm can search large, unstructured databases faster than any classical algorithm, making it useful for optimization and AI. But perhaps the most exciting area is simulation. Quantum computers could simulate the behavior of molecules, atoms, and complex chemical reactions, something classical computers struggle with. This could accelerate drug discovery, material science, and even climate modeling. For example, a new medicine might be discovered not through years of lab testing, but through quantum simulation in just days or weeks. In 2019, Google announced it had achieved quantum supremacy. Their machine, called Sycamore, completed a complex computation in just 200 seconds. Google claimed that the same task would take the world's fastest classical supercomputer over 10,000 years. IBM challenged that claim, saying it could be done in a few days on a classical system. But the message was clear. Quantum computing was no longer theoretical. It was real. It was happening. And the race had officially begun. Many people think quantum computing is still a decade away from being useful. But companies are already finding early applications. Volkswagen is using quantum algorithms to optimize traffic flow in cities. JP Morgan Chase is using quantum models for financial analysis and risk management. ExxonMobil is running quantum simulations to improve battery chemistry and fuel efficiency. Microsoft and IBM now offer access to quantum processors through cloud platforms, allowing researchers and developers to experiment without owning the hardware. The US government, the European Union, and China are all investing billions of dollars in national quantum initiatives. They know the potential is enormous, and so are the risks of being left behind. In late 2023 and early 2024, both IBM and Microsoft released updated roadmaps for quantum development. IBM aims to build machines with thousands of logical qubits by 2030. That would be enough to solve meaningful, real-world problems that classical machines simply can't handle. Microsoft is pursuing a different approach using topological qubits, which are theoretically more stable. Their goal is to achieve fault-tolerant quantum computing, systems that can run reliably for long periods without crashing. By 2030, experts predict that quantum computing could be used for things like designing new materials, creating more powerful batteries, developing sustainable fertilizers, optimizing logistics, and even improving weather forecasting models. This is not science fiction. This is the direction we are heading right now. So, why should you care? Because quantum computing could change everything. It could affect the security of your online data. It could determine how we fight disease, how we respond to climate change, and how we manage global supply chains. It could lead to faster, more capable AI systems. It could bring scientific breakthroughs that we can't even imagine yet. And just like the internet transformed the world in the 1990s and 2000s, quantum technology might define the next era of human progress. Understanding it now gives you a front-row seat to one of the most important revolutions of our time. Quantum computing is not just about faster computers. It's about unlocking a new dimension of thinking. It challenges our understanding of logic, information, and even reality itself. Whether it's solving problems that affect millions, curing diseases, or securing the digital world, quantum computing will be at the center of it. The question is not if it will happen, but when. Thanks for watching. If you found this video interesting, subscribe for more science content and let us know in the comments what excites you most about the quantum future.